Hi, thank you everyone for coming to PyBay 2019. I hope all of you enjoyed the lunch. Thank you. So it is my great pleasure to introduce you to Alice Wang, our speaker today. She has a background in ad tech, in biddable media, and it's biddable media and ad tech that actually got me into programming. So I am super excited to hear about what she's been up to, because in kind of a very roundabout way, she's been very influential, like in the work I do. So please give it to Alex Wang. Thank you.
Thank you, everyone, for coming. Am I coming through clear? Okay, great. So today, the talk that I'm giving is on real-time bidding models in computational advertising. A little bit about myself. I'm currently working as a senior data scientist at even.com, a fintech company based in Oakland, whose mission is to end the paycheck-to-paycheck cycle. Previously, I've worked in various different domains in the ad tech space for an ad exchange, as well as on the demand-side platforms, both in the web and mobile space. Subsequently, I worked in sales tech and gig marketplace and fintech, and I'm happy to speak with you about applications of data science and machine learning in any of these domains. I'm curious who you are. Please raise your hand if you're a product manager or a project manager. Hi. What about data scientist? Yay. What about data engineer? Hi. And backend engineer. I guess you can be both or multiple things at the same time. That's great. OK, cool. So this particular talk will probably be relevant to you in some of your day-to-day workflow and product development cycles. And I will be kind of going into detail on any of these things that you might be interested in. Let's start with newspaper ads. So this is a newspaper, and there's ads on it. The way this used to happen is that businesses will purchase an ad slot on a newspaper, and the paper will get printed, and everyone who sees the same edition of the newspaper will see the same ad. In today's world, that is no longer the case because of computational advertising. Ad slots are bidded on programmatically and dynamically by advertisers, so that each person who goes to the same landing page will actually see different ads served to them because of behavioral targeting. And that's what we'll be covering today in our talk about exactly how that happens. A little bit of statistics about computational advertising. It's been around since the mid-2000s and impacts pretty much the entire US population that is on the web today. It is in the space of big data. There's about 100 billion bid requests made per day, and it takes about 100 million seconds to serve an ad impression. And we'll be revisiting that idea throughout this talk. Vocabulary terms, an advertiser. An advertiser is interested in their customers, advertising to their customers so that a good or service can be purchased. A DSP, demand-side platform, is an agency that represents advertisers to help them manage their campaigns to target to the right users. An AdX is a lot like a stock exchange. It matches buyers and sellers for each ad impression. An SSP, a supply-side platform, is analogous to an DSP for advertisers in the same way that it is for publishers. And publishers, in this case, is a website like bbc.com. Data management platform is a management platform that sells user browsing history information to DSPs so that the DSPs can improve on their user targeting. And RTB stands for real-time bidding. Just want to reiterate that the fundamental goal in computational advertising is to programmatically deliver the right ads to the right users at the right time at the price determined by the ad exchange. Here's an overview of the RTP ecosystem. A user interacts with the publisher website, bbc.com. The publisher website interacts with the ad exchange, and the ad exchange connects them to the DSP. The DSP may choose to augment the user data in addition to the bid request with the data exchange. And subsequently, the user sees the ad populated on the publisher site. Zooming in a little bit, what does this experience look like from your perspective? As a user, you're loading a web page, and there's an ad slot on it. At the same time, an ad request is made to the RTP ad exchange, and a bid request is then made from the RTP to the DSP. It's not shown here, but there's actually many different DSPs. Each DSP will use the user's page and context data, augmented with the demographics, segment information, such as user interests and browsing history, and compute that in a model and return a bid price. All the DSPs will do this, and an auction will happen again at the RTP ad exchange. It's called a second price auction. The highest bidder wins the auction, and the second highest price is paid. Subsequently, the ad with tracking is served onto the publisher's site, and this all happens within 100 milliseconds. Subsequently, the user's feedback in terms of clicks and conversions will then be sent back to the DSP. And this sums up user behavioral targeting. If you think about it, have you had the experience of browsing on the web where you went on a web page and left without doing anything, but then subsequently maybe the pair of shoes you might have looked at followed you everywhere else on the web? As annoying as that might be, what's actually happening is because of the ecosystem and under the hood, the dynamic pricing and ad bidding that's happening in the background. So the ads that are placed onto the subsequent pages that you're on is happening by no accident. DSPs actually see that browser history and know that you might have potential interest in making a purchase and will bid on you and in terms of the ad slot to try to bring you back to the original site to make a purchase. So that's how it's happening. Real-time bidding is the process that facilitates the buying of an ad impression in real time. Using user behavioral targeting, a second price auction happens amongst the DSPs, and the KPIs that we are particularly interested in from the DSP's perspective in managing a budget that's constrained by how much advertisers are giving them are events like click-through rates and conversions. Conversions or examples of that may be purchases or app installs. User response prediction. Before we dive into that, I just want to restate the goal here. The goal in advertising, computational advertising, is to deliver the right ads to the right people at the right time. So the input in this particular case, for those of you who are data scientists, is that you get input features by way of the bid request, the browser's context, augmented with the user features about past history from the DMP. And the output is the probability that the user will click on an ad impression. What does that look like? For non-data scientists, a set of user features can be these bullet points, such as time of day, the IP address, where the user is located, the URL, what browser they're browsing from, even the ad size. And additional information such as user tags are being queried for via user syncing from the DMP. In order to create a model, we have to convert this data first into a feature matrix. And the target vector in this case are labels such as click or no click. So I might have hinted that click or no click, in order to treat that, we would want to use a supervised learning method such as classification in order to create a model, an RTP model for predicting who are the right users to serve an ad to. To do that, essentially in the two feature space here, represented by this graph, let's think of the green dots as no-click events and the red dots as click events. We are looking to create a model such that the decision boundary between the two different classes are such that they're separable and predictive. So again, the input here is the bid request and the user features, and the output is the probability the user will click on an ad impression. And we do this by using classification. There's many ways to do this today. I would just go over how logistic regression does this. We will not be discussing other methods, but that is also used in production today at many different DSPs. Let's talk about the sigmoid function. The sigmoid function essentially converts or maps any value on the real line to a probability in the range of between 0 and 1. So here you have the formula of 1 over 1 plus e to the negative t. T in this case, when we expand it, could be the linear regression function, and essentially it forces any value that's continuous into the range of 0 and 1. We're particularly interested in this exercise for the purposes of classification, which is a review for those of you who are data scientists. But traditionally, the threshold is set at 0.5, such that essentially any probability predicted between the 0.5 to 1 range will be considered the click class, and anything below that will be the non-click class. There's a couple of considerations when making RTP models that are specific to the ad tech domain. The first is imbalanced training data, and the second is categorical data. What I mean by imbalanced training data is that you can imagine many people, including yourselves, view ad impressions every day, all the time, but never click on them. This has implications downstream in terms of gathering training data and creating predictive RTP models. 0 in this case is basically no click, and 1 is click. The other thing is, as I'd shown previously, a lot of the user features and bid request data comes in as non-numeric values. We have to treat this by basically converting or binarizing them in machine learning terms. So in this particular example, color strings are converted into 3 different columns with zeros representing the lack of existence of them in the particular row instance, and 1 meaning that they are present. A brief review of a confusion matrix. Essentially, we're particularly interested in the case of binary classification, how well the model predicts in terms of our model. So in the particular case, if we have a cat and we predict towards a cat, that is considered a true positive. And if we have a dog and we predict that it's a dog, it's considered a true negative. We calculate precision and recall based on the contingency matrix in the previous slide. And these are particularly good measurements for how well our RTP model is doing. So precision is a measure of how good your positive predictions are, and recall is a measure of how well you predict the positive classes. From the user's perspective, precision perhaps may be more important because you don't want to be shown ads that are irrelevant to you, or any at all. Recall is particularly interesting to the DSP itself because you're trying to turn a profit. How well you predict the positive classes has implications for you in terms of how well the user converts. One additional metric that we use to evaluate our model is area under a curve. It's another way to evaluate the classifier. And the important key note to emphasize here is that the dotted line represents a model that is as good as random guessing. So the aim of any machine learning model is actually to be above the dotted line, in this particular case, as close to the area equals to 1 as possible in this particular case. I'll be touching on this again in code, so we're going over this because we'll be looking at it again. So before we do that, in terms of model architecture, I just want to point out that all of the model training is done offline, and that is still the case today. There is some online training in terms of academic research, but in terms of actual production, model training is still done offline. So in training the model offline, it is stored, but then in terms of online requests, the bid requests and user data is sent to the featurizer to then be represented in matrix vectorized form, and then the model is applied to the particular user represented by the vector, and the bid response is then returned in terms of price contingent on the probability of the click event for that particular user. This being a Python conference, I just wanted to show some code. And also, I've reused this code time and time again in different scenarios. We rely on the open source library scikit-learn to basically run and generate a model using logistic regression. I want to point out that in calling linear model logistic regression class weight equals balanced, what we're doing here is treating the class imbalance issue we pointed out earlier. Class weight equals balance essentially flips the proportion of the minority versus majority classes such that it weights or gives more weighting to the minority class. The minority class in this particular case is due to the fact that within our training data, we don't have a lot of click events in comparison to our non-click events. We're also interested in the average AUC, and here we have a for loop that essentially loops 10 times for a k-fold class validation. It is a method that prevents overfitting in your machine learning models. Subsequently, we split and the training data into train tests, with the test data set being 20% and the training data being 80% of the original data set. We fit the data to our model, and we make predictions on our holdout set of 20%. We compute metrics for the route curve, and in particular AUC, and we sum that up and divide it by the number of folds that we have. Overall, model.fit XY happens when we decide that our model is actually deemed to be predictive towards our purposes for predicting user clicks. Just want to point out one more thing with online model prediction. Logistic regression is popular for another reason, in that the model itself can be outputted as a set of coefficient values and corresponding intercept. So for any new user, you can just apply the logistic regression function using the weights that you've set aside ahead of time. And in this particular case, X stands for the vector of user features and the bid requests. And you're basically applying the dot product between that and the beta. Beta is essentially the weights that you have in the exponent here for the linear regression function. This is important because online prediction may not actually happen in Python in a lot of scenarios, especially because of the 100 millisecond constraint. Online prediction is done in some other programming language for performance reasons and for scalability. As a recap, today our talk dived into the ad tech ecosystem, how DSPs optimize and ad campaigns for advertisers using user behavioral targeting and real-time bidding, applications of machine learning in optimizing click-through rate, as well as modeling challenges and how to evaluate the models, and ultimately how to deploy models at scale. Thank you. Questions?
Would you like to answer some?
Sure. Questions?
Yes. We have some time for questions. 1 second. So some hands up here.
I wanted to comment on the 0.5 threshold that's set. My experience is, as you're training a model, the threshold moves, or at least what you perceive as of the class and not of the class. Why 0.5, or do you move that in production?
Oh, right. So he's talking about this slide. This is just a slide to demonstrate how logistic regression generally works. I understand that in production settings, you may tweak the threshold. So in this particular case, I didn't dive further into it because I didn't know how many people attending would be actually data scientists.
So this might be kind of outside the scope, but so when you said there's 100 millisecond from request to response for the user, right, for the ad?
Sorry?
So there's like 100 millisecond request to response for the user. So like the user loads a web page, and then in 100 milliseconds, they've got the ad on their web page. Is that how it works? Yeah?
Yes.
So like, I don't really know how to ask this question, but how exactly is it so optimized? Like how
Can you
is it
speak
100
louder? Sorry.
But it's like 100 milliseconds, which is a very short period of time. So how exactly is it that optimized? Like how is it that fast?
How is that optimized?
Yeah.
So this is out of scope in the sense that I think for basically, as a user loading a page, API responses are like considered to be slow if it's in the second range. And so essentially this entire flow here happens within that as a time constraint. Because what needs to happen is the auction also needs to happen amongst the different DSPs. And so I guess it depends on like which part of the optimization you're talking about here. Basically, DSPs work to make sure that they meet that time constraint. Otherwise, they won't be able to return a bid response or a bid price back into the auction itself for the auction to actually happen in the background. So the entire flow here back and forth from the time that you're loading the page to when you get served an ad is 100 milliseconds. In fact, because the Wi-Fi here is a little laggy, I tried to take a screenshot earlier, and the ad itself took a little bit longer than the rest of the page. That was cached in the browser. Yeah.
Yeah, could you talk a little bit more about the machine learning you use? In my experience in this is that we've had hugely imbalanced data sets, and I've used something like SMOTE I don't know if you use that or if you use like split vector machines or something else besides just a ordinary least squares regression, logistic regression fit.
You're talking about like upsampling, downsampling?
Yes.
Yeah. So that can be used. I think in production settings when we have used it. So what he's referring to is when you have imbalanced data, can we have other methods to treat the class imbalance issue such that we basically bring the two bars up to about the same level in terms of labels in our training data set. SMO, I think that's upsampling, right? SMO, upsampling, and downsampling are techniques that can be used. So your specific question is, like, has that worked well? Yeah, so I tried it. It worked okay. Yeah, so it's not like, I wouldn't say it really moved the needle or anything like that. There were questions here.
Hi.
Oh, sorry.
What's your opinion around causal modeling or causal inference in advertising around real-time bidding? Because maybe from a business perspective, just optimizing for CTR might not be the best thing to do.
Causal inference in terms of click-through?
In terms of click-through, right? Like,
You mean in terms of attribution?
yeah.
Okay, so what he's referring to is you might be shown an ad, and then you get shown that ad again and again, but in terms of attribution, like which ad was it that you were shown that ultimately led to that action? I believe the way it currently works in ad tech is the last impression you saw. So you might have seen the ad, you know, like 5 web pages ago, and it was shown to you anytime in between that ad and the current ad, but that's the ad that actually happened to have been shown and to have clicked on. I think it is difficult to establish the causal relationship. So that's an approximate way to do it. Hi.
This is a follow-up question to piggyback the upsampling.
Yes.
I'm also dealing with imbalanced data sets, and I'm just wondering for you, like what kind of technique is most successful?
So this one, sorry, this particular one, basically weighting towards the, so I'm guessing you're a data scientist, so it's weighting towards the minority class, because essentially you want to be able in your confusion matrix to be able to produce true positive events in this case, right? The model could say it's like 98% accurate, but you're mostly predicting towards no-click events, which isn't very useful to you. And from the advertiser's perspective, they're particularly interested in how well you predict the positive classes. So you say, my model predicts 0, you know, clicks most of the time. That's not particularly useful from the business, right, standpoint. So that's one technique I would use.
You mentioned that in the bidding, like the winner pays the second highest price.
Yes.
So I was just wondering what the effect of that structure is on, say, you know, the market and how prices go up and down.
Yeah, so I think it has somewhat of a smoothing effect, right? And also, one thing I didn't mention here, because this talk mostly covered DSP and not SSPs, is that, you know, whatever price gets set, the SSP has to agree. The SSP has a threshold for like what the minimum price they're willing to accept. So if a bunch of DSPs enter the marketplace and just like bid super low, and then so happens the highest price of the set of really low prices wins, the SSP is not obliged to accept it, which is why the price is set by the marketplace. In which case, if nobody is able to bid on that ad slot, the ad slot gets turned to a non-RTB exchange. So it will leave the RTB space into something else that we didn't get to cover. You can read more about second price auctions. It's called the Vickery auction. It's different from a first price auction.
Well, thank you so much. Everyone give her a big round of applause.